Good evening, everybody. Can you hear me okay?
Hello.
Excellent. I'm going to start desktop sharing. Welcome. Can you all see the desktop okay? Okay, let's see who we have here tonight. Albert, Boomer, Daniel, Fang, Kang. Welcome. And Mega. Welcome. Tonight, first, I guess, are there any questions before we begin? Once again, you need to use the chat window to ask questions. Okay, we're going to finish up Chapter 2, and then I've got another resource I wanted to use. Welcome, Karen. Just a different perspective. Homeworks 1 and 2 are due this Sunday, the 21st. Don't forget to log into Canvas by this Friday, or I will drop you as a no-show. The CC Confer question I'm going to answer on Thursday, so it's not going to be available until our session Thursday evening, and then I'll answer it during that. And there's a test this week on chapters 1 and 2. It opens on Friday and runs available through Sunday. The first part, there's two parts to the test. Maybe I should show you that. I'm going to review that with you on Thursday. But there's two parts to it. The only way I could do optional was to split them into, this is required, 45 points, and then this is optional, worth up to 5 points. It's the only way I could do the extra credit on a single test. So this has a 2-hour time limit, and this has a half-hour time limit. Because the tests get a little more difficult over time, you'll get a little more time with each test. We're going to have 3 major tests, and then the final. Once again, the homeworks are, and these CC Confer questions and these homeworks, they're all under quizzes. So basically, most of the work is under the quizzes title, this here, quizzes on Canvas. The other thing is there are discussions which I've started to read and reply. I hope you get those. You're required to do 4 during the quarter. We spent time talking about the hardware. We'll spend some more time on that. At the end of next week, we're going to kind of move away from the hardware stuff and talk about the functions from an algorithmic perspective in the operating system. But I really wanted you to understand how the operating system interfaces with application code, user activities, and hardware activities. So So how does it all work together? And you really need to understand pieces of the hardware. And mainly we're talking about the CPU, because that's the controller of the computer environment. Okay. I did note that a few people have completed question 1, and I graded it. But it's not due until the end of the week. Are there any questions on the work? Do you have any questions on that? Or, you know, how this stuff works? Albert, do you have a question? Okay. Go back to the agenda. Okay, I'm going to finish chapter 2. We left off on slide 46. And then I'm going to review another resource I have. Just to try and emphasize it from a different book's perspective. These things I provide you are good examples of if you want to dig in and see from a CPU perspective how things work. Let's see where we are on chapter 2. We left off at 46, but I wanted to pick up at 41 again and review that real quick. Have any of you not used a virtual machine? Okay. What you can do to kind of see how it works is I would install a freebie one, like Oracle's VirtualBox. I found to be pretty good. There's a Virtual PC by Microsoft that will work. But what you want to do is just install it, the product, and then what you would do is you would it's VirtualBox, Oracle's VirtualBox. So you could find that on the internet like I did, download it and install it on your box. What's nice about this environment is I believe it also works. Yeah, it does, because I tried it on Linux. I don't have a Mac, so I haven't tried it on Mac, but I would assume it works as well on a Mac. But then you can install an operating system, and the way I would do that is I would, like for example, Ubuntu is a freebie. You could download Ubuntu ISO file. It would be an ISO file, and then when you click New here, you put the name, and then you put the operating system type. And it would be Ubuntu would be Linux, but you could install other things. Now, I happen to have OS2. Maybe I should install OS2. You guys probably don't even know that exists, but I bought it back in the late 80s. I'll talk about it when we talk a little bit further about OS2. Anyway, you would install it, and they would ask you about the what file to load, and ISO files would load it nicely. That's what I did with Ubuntu. And then you can play with it a little bit. All of this stuff is just extra for you for experience. I think the more that you can play and learn by trying, it's worth it. Yeah, Hyper-V. Yeah, that's right. And when we talk about more stuff, I'll be bringing this back up again. Okay, but that's what the idea is. You would have, like on this, right, you had the environment, which is a single operating system, for example. So you wrote up the single operating system and the kernel talks directly to the hardware, and then the programs run on it. And that's what most people have, is a single operating system. If you had a virtual machine, what you would do is you'd have the virtual machine kind of talking through these little stubs here, these VM1, VM2, VM3 stubs, to the kernel of whatever operating system you load in that partition. And the way most of them are implemented is, I'll just show you real quick. On my machine, I carved out a drive. So what I did was part of my C drive, that's, I don't know, 500 gig or 600 gig, I carved out 3 drives. One was the C drive where I, install all my programs, and then the E drive is all my data. So all of the school's data files, all of my source exe files are sitting on the E drive, so I could back that up easily. And then I created another partition for my virtual machines. We carved out, looks like not much, 150 gigs it looks like. I carved out 150 gigs. And then I'm using, I don't know, 13 gigs of them. But the other day, tonight, I put a virtual, these are some more virtual boxes, I just did that tonight, for an ISO concept. So I'll come back to that later. I haven't finished playing with it. But that's what you do. You kind of play with something and you learn how it works. Okay? On these virtual machines, you can't really hurt them too bad. You just got to be careful about your host machine, where this thing resides. All right. Any questions on that? Okay, so it's just explaining how various things are used in these container objects. Like I said, Solaris is gone as an operating system. It's a good example. I thought it was a great operating system. VMware architecture, how it works. It's a very good product. Costs money. I suppose to answer Boomer is that the program, like for instance, I'm running this virtual manager, right? And so if you go to, in Unix, it would be a process just like it would be in Windows. and then you would find that process, right? You would find that VM process, and I'd have to find out its name. Here it is, Virtual Manager, and that's the process. So yeah, you could kill the process, and that would of course kill any access to the virtual machines. But the problem with doing that is it doesn't close them properly. So I can see where it might spin out of control, but if you do kill it, it's in a state, right? The files that are opened by the program are in a specific state of the machine, and you're going to lose that state when you kill the main program that is your virtual machine. So you just got to be aware of that. You're welcome. Yeah, what I do with my virtual machines, let me think. Look at them. I've got this saved, and I've got that saved. And this one's powered off, and this one's powered off. If they're powered off, you don't have to worry. It's only when they're running. Like this is saved, so I could kill this whole thing and not worry. But if it's running a virtual environment, and I kill it, then I might have some issues. Yes, I might have issues. But it would be with the virtual machines. It wouldn't be with my machine, not typically. All right, well, once again, this is the environment. It's kind of cool. And the Java virtual machine, I was going to try and illustrate this a little bit better, but my Java code was my J creator. I ran out of license on it, so I was going to demonstrate that with you guys. But I think you all know how Java works. It's another program that runs, and on Windows it runs as a service, and I guess it would be a service or a process on Linux as well. Okay. When you're looking for bugs, there's typically log files for everything. So let's take a look at Windows. And typically it would be in your C drive in Windows. And there's this performance logs, and I'm not sure if that's Windows or some other facility. We'll talk about security. There's nothing. So it's not Windows. It's some other software I installed that uses that. But you can see there's logs here. I don't know if you can see that. It's hidden. This is looks like a hidden file. Let's look at the properties. No, it's not hidden. So that's a good thing. So you can see it. That's why I'm showing hidden files as well here, so I can see some of the stuff. And it might be under Windows. I was just looking for where it might log stuff. Here's logs. And yeah, this would be logs of all kinds of stuff that's going on in your system. Every operating system has one like this, or an area where it logs stuff. One of the nice features, I think, of Windows is the event log that you have available to you. At some point we'll show you that. Core dumps typically occur at some point. It just gets typically this would occur when the operating system doesn't have a trap set for that error. In other words, it didn't set any error traps, and it ran into a machine instruction that it didn't expect an error. Well, then you would typically go to a core dump for that process at that time. Same thing for crash. And they all have issues. Operating systems aren't perfect. Matter of fact, the more complex they get, the more issues arise. When you, let's say, when you're installing Windows, let's give that an example. When you're installing Windows, what it's really doing is it's establishing on your particular hardware what the right drivers are that need to be activated and loaded. And that's really called a CIS31, where you install the operating system. And it configures the hardware. It makes sure that the software drivers are the correct drivers for that. And that's why it takes so long to install Windows. I don't know if you've seen it. It's gotten better over the years, actually. I remember Windows 3.1 was easy to install. Windows NT was a little more complicated, and then Vista took quite a while to install. Windows 7, Windows 8 seems to take forever. And when I installed Windows 10 on the virtual machine, it took a while. So it takes a long time to do this CIS31. That's really installing the operating system and configuring it on the specific hardware. Then there's a booting process, right, that boots the computer. And I'll share on at some point how that works. Probably when we talk about memory or something. The bootstrap program is stored on ROM, and usually what that is the I/O subsystem that speaks to the devices is usually coded in here, and that's in ROM, read-only memory. So basically, when the hardware first starts up, when you do a boot, right, it hardware-wise knows it's a physical startup, and it sets a flag to the CPU, and it fetches the instruction from ROM, not from RAM, and then the ROM looks and loads the program into whatever memory you've got. And that's really the process here. It's just the kernel, and it loads, I would call it the boot program. It loads the boot program, which loads the kernel and other stuff. And I'll share that with you too, because next week when we go through process management, I'm going to illustrate the starting up of the computer and what gets stored where in memory in order to run properly. Talked about the bootstrap loader. And it's typically a multi-step process. And that kind of ends chapter 2. Now I have another presentation from a different author. And I used this book for a while. I didn't put it on Canvas because I don't typically use this book, but this is just a different author going through the same material, and I thought it might be good to see what this author uses. I used this for about Stallings for about 3 or 4 years. I used this book, and then I went back to Silver Shots. Prior to that, I used Detail's book for 10 or 15 years. That was really excellent. But the problem with this book was his problems were so complex. They were really tough to do, where Silver Shots are a lot easier problems for students to accomplish. So let's go through this one. Basically, it's talking about the same elements that was in the other Silver Shots book. So, program controls the execution of all the application programs and an interface between applications and hardware. I think we've said this before. The objectives, convenience, efficiency, ability to evolve. And I noticed that on some of your comments on operating systems, you guys all kind of led into what kind is a good operating system. That was a good discussion. I followed that. And you guys brought up all of these ideas. And what you want to do is when you look at an operating system, you want to see what were their design objectives. Because when they choose different algorithms of implementation for different of the rules of the operating system, they have to choose it to meet their design objectives. And that's going to be part of what we're going to be learning. And you're going to have a project that you're going to do as a team. 6 to 7 of you guys will be on a team. And what you're going to do is you're going to evaluate the operating system of your choice for certain characteristics. And I'll talk more on that. But it has to do with the objectives. Okay, we've seen this diagram before. Application programs, right? You have this interface, this layering. Application programs, you got utilities. You have your operating system. You've got your executing hardware. I assume that this is the CPU. You have memory, translation, so some kind of memory management unit. You have your interconnection bus, that's more hardware. And you have your I/O devices, your networking, and main memory. So all of this you've got going as part of your hardware, and the operating system manages it all. It's got to manage all of these layers of things. Services. It provides many services. Program execution is one of the main ones. Program development, of course, would be the utilities, right? The C language compilers and all of the things that go that are provided for by the OS. Typically, languages aren't provided, but I think that there's in Windows today and in Linux you have the shell capability of writing shells. Well, that's a programming language if you write a shell, because it has certain rules, mechanisms. So you could say this is some program development, I guess. Access I/O devices, yeah, you got to be able to do that. You want controlled access to files. You don't want people gaining access to files that they shouldn't be. The system access to everything. error detection, response, and accounting. You have an architecture, right, that is a set architecture that you need to work with, and then you have a binary interface from the application, and then you have a programming interface, an application programming interface. And to illustrate this one, I have a different, let me see. Thought I had a different diagram. Oh, shoot, I can't see it now. I must have closed it. Well, I'll come back to it after. Complete set of resources, storage and movement of data through all the different devices. Let's see, what else? Program or suite of programs executed by the processor, so that's part of the operating system. And it's saying as software. How does it look as software? And it frequently relinquishes control and depends on the processor to allow to regain control. So basically what we mean by that is it turns control over to the CPU to execute instructions, and to get control back, the processor has to somehow return to the operating system. And that's the integration piece I want you to really understand in these first 2 weeks. And I think they're showing it here. You've got your operating system, you've got the OS in memory here, and you've got user programs running here. Okay. You got an I/O controller. You got your printer, your keyboard, your scanners, all those other devices. Okay, and you might have another storage device, a disk, SSD, whatever is external storage, and you might have a couple of processors, one or more processors. And what you're doing is your operating system as a resource manager. And those two words really key in my mind of what an operating system is. And what this is trying to say is they evolve, and that's a real fact. Windows 3.1 was a non-preemptive operating system. When we talk about processes, chapter 4 or 5, I can't remember where, we're going to talk and describe operating system in terms of preemptive and non-preemptive. Well, Windows 3.1 was non-preemptive. Windows 95 was non-preemptive. It wasn't until NT came out that it was a preemptive operating system. So what they're talking about here is that the operating system evolves and gets more complex over time. And that's just one concept. Here is new types of hardware. Well, what wasn't available, give me an example of hardware that's really readily used today that was not used in the 1980s or 90s. Anybody have one? Can anybody name one? Portable computers. No, they were available in the 80s. Touch screen, they were available in the 80s. iPad tables. iPad. No, there were devices of that nature in the 80s. Think of more generic Well, that's one. Bluetooth, that was not available in the 80s. Wi-Fi, yeah, that's another one. Yeah, a lot of apps, but I'm talking hardware, not software. Apps are software, in my mind. Yes and no. Kang, yes and no. There were some, not true virtual reality, but what there were in the 80s was expert systems, very similar. They weren't physical devices, though. Kurzweiler. There was a Kurzweiler artificial intelligence machine. That was hardware. No, what I was thinking was USB devices. USB devices are pretty common today. They were not common in the 1980s or 90s. CDs came around in the 90s. Right. DVD was later, along with Blu-ray. Yeah, but there are. It has to be able to handle those new types of hardware. Okay. And new services, like you guys mentioned, apps and VR devices and stuff, new services. And of course, you got to handle fixes, especially if you're a Microsoft. From an evolution of computing. Yeah, right, thanks. An evolution of computing means starting from the mainframe. Mainframe was very serial processing. You would stick a program in, it would run it. You'd stick another program in, it would run it. And then simple batch systems, also mainframe, meaning I could put in a series of one batch job, and that job could run many programs, but only one program at a time. Then they developed multi-programming. I could run more than one program at a time. And then this idea of time sharing is time slicing the CPU for many users to be online getting access. So that's one evolution. What you don't see up here is the internet, because basically the internet is this environment. The internet we have today is time sharing on a system. You know, you go to Google, you ask them a question, they come back. That's timeshare. It's not called that, but that's what it is. That's how it's implemented. And the earliest computers had no operating systems, but just control programs. Okay. Batch means it runs a series of instructions at one time, or a series of programs at one time. I'll talk more about monitors in Chapter 6, and I'll illustrate that, and kind of why we need monitors. You could still use them. As a matter of fact, I think this is a good approach to small systems like automobile systems. They would use a monitor type operating system. Control sequence of events. Monitors are really designed well for that. There's typically a resident portion of the monitor, and then it reads in work and gives control to that user program. Okay, and the way this one works is you've got your interrupt processing area, your device driver area, your sequencing of your job area, and then your language that the user would enter to run this environment. So the command, the language interpreter, is the interface to the user to submit work. Okay, and I mentioned that last time to you guys, right? The command line interface. We'll talk more about that concept. Let's see, what else we got. And what we're doing is we're looking at this environment from different points of view. That's why I kind of like this alternate way of looking at something. The processor executes instructions from memory containing the monitor. Execute instructions in the user program until it encounters an end or an error, or a request. Here, control is passed to a job means processor is fetching, executing instructions in a user program. Controls return to the monitor means the processor is fetching and executing instructions from the monitor. So this is a simple environment to manage. Job control language, JCL. This terminology came from the mainframe, IBM, and all the big iron guys still use job control language to execute. Let's see. Now, what features do you want your hardware to be able to do? You want memory protection for the monitor. So basically what you're saying is while the user program is executing, it must not alter memory area containing the monitor. That's memory protection. You need some sort of timer. Prevents the job from monopolizing the system. So you need to have a timer. And this is critical in a multi-programming environment where I want to run more than one program at a time. I got to have a timer. The concept of a privilege instruction can only be executed by the monitor. You do not want the user program to execute privileged instructions. You do not. And on our homework for week 1, works the same way on multi-threading as it does on multiprocessing. On chapter 4, I'll talk about threading, and we'll see it then. Okay? Good. On our homework, first homework assignment, I have a question here regarding which instructions should be privileged instructions. And most of the people that answered that got it correct. They correctly identified the right instructions. But the idea is you only want the operating system to execute instructions that affect everything or affect hardware in some way. Okay? Interrupts. The operating system is more flexible in controlling user programs. In other words, if the user program wants service, wants to open a file, read a file, write a file, whatever it wants to do, it needs a way to tell the operating system to perform that service. So the way to do that is to generate a software interrupt. And that's called a trap or a software interrupt. Or on the mainframe, it's called a service request. It doesn't matter what it's called, but the idea is it's an interrupt, and the hardware mechanism takes control. And next week, I'm going to illustrate more in depth how that works. We talked about this before. There are 2 modes of operation. There's the user mode and the kernel or monitor mode. And the CPUs of today handle that pretty well. And I wanted to share that with you somewhere. We talked about it. Let me see. Hang on a sec. Yeah. I'm going to put this link on our chat window. And why I like this particular link, I didn't put this in Canvas, but in my browser here, I have OS links that I like, and I have these that I'm going to share with you over time. Okay, well, this is one of them, and I'll stick them here for you to use at your convenience. I'm not going to put them on Canvas, but it's got the different, like real mode, what that really means, protected mode, protected virtual address mode. Some of these things didn't exist in the architecture. Okay, not until the 286. The original 88 and 8086 processors did not have multiple modes, you know, for privileged instructions and non-privileged instructions. It wasn't until the 286 came around, Intel's 286, that this protected mode had interrupts that allowed things to work. And if you read through this architecture, and I highly recommend you reading through some of this stuff to see how it really works. Okay? I'm not going to do it in depth with you, but it explains it pretty nicely. So you look at that architecture. And then you've got the AMD, right? You want to take a look at the more current architecture, or you want to look at Pentium and how that guy looks and what was added, what features were added, and how it works on mobiles and things of that nature. Okay. So there's information here if you're interested in delving into it. And they're talking about the multiple cores and when it was released. I mean, these are older. Looks like they're pretty old to me. About 10 years. But they're there. They're available to you. And that's where you get the idea of kernel mode and user mode. Without the hardware, you won't be able to support that. So when you're in kernel mode, you're basically this is software, but you're also in the hardware CPU mode of privileged instructions. You can execute privileged instructions. So when you're in the kernel mode of the operating system, you're in the hardware privileged mode, and you could run any instruction. Then when you start up a user program to run, the kernel starts the user program, it flips mode. When it starts the program to run, it flips mode back to non-privileged CPU mode. And now the user program can't execute privileged instructions. Okay, does that make sense? I didn't get any yet. Oh, I did get a yes. Thank you. I mean, is anybody confused about that? To me, that's one of the key concepts. Yes, Kang. Let me start my MS-DOS. I showed you this last time. It's easier to see it on a simple operating system. I'm going to go to the C drive. And I want to show you. I'm going to do a directory. What I did was, the way this virtual box, this virtual machine works, is the A drive is protected. I can't change the A drive. So what I did was, I created, on the virtual machine, I created a disk to be able to use, and the virtual machine, as part of the virtual machine. So I created this C drive, and how I did that was I used fdisk. So fdisk is format disk, and I'm going to display the partitions on the disk, and I created a C partition. It's 400 megabytes, and it's a FAT16 file system type. Okay, that's what I created, and I could delete that partition. I could delete that partition using this system. So what happens is, when I actually enter the code, this program is part of the operating system, because there's no concept. There's no concept like what we're talking about here. By that I mean, these two things don't exist in a DOS world, because everything is kernel mode. So everything I run here is in kernel mode. There is no user mode, because of the operating system so old. All right. So let me move to an operating system. I'm going to. I got it. All right. I'm going to close this, and I'll turn it off. Okay. And I'm going to start this one, XP. Now I save this, means I save the state of the machine, and it's going to restore the state. And I did this with you last time. I showed you a program. These are machine instructions right here. This is machine instructions, and they all do certain things. And this is the assembly. This is what you would put if you were writing an assembler code. You would put pot or push CS, and it would push CS, the CS register on the stack. But you see this int right here. As soon as you hit this int, it's a hardware interrupt, because it's a software interrupt, because you're writing a code right here. So me as a user, because I'm a user program running in non-privileged mode, I put this int21, and as soon as I do that, the operating system gets control, because this interrupt flips to kernel mode and goes to the operating system that handles this interrupt. I'll show you how that's done in Chapter 3. I'm not going to show you now. But that's what's happening. So right at this level here, when it hits this, it goes away from this program. The operating system gets control, does this function, and returns control right here. So now we're back in user mode with non-privileged instruction, and the next thing I execute is this move, which I move an address into the AX register, whatever's at that address. And then I do an interrupt again, okay, to get a different service. The first service was, I don't know, 09, and the next service is whatever's at that address. And do an interrupt 21, and I'm back in the operating system performing that request, and then I'm in privileged mode performing the request, and then I return control back, and I do a push of the system pointer. Apparently I push it on a stack, and then I do this DB and jump if binary something 0 or something. And that keeps going. And I'm in user mode and non-privileged CPU mode. Is that clear? Yeah, jump not below. Thanks. I haven't done this in a long time. You're close, Vega. You're close to the idea. On a virtual machine, what happens is it is operating on the OS kernel, in OS kernel mode, but what happens is it passes that request to the real host operating system. Let me see if I can I think we saw that here. Let's go back to this. You see this right here, this VM1, VM2, and VM3. That converts the request, right, to the instruction of the machine, and then this is the operating system on the host that performs the function. So that's how I visualize this working. It's got to end up going through the host to get to the hardware. But this is the host operating system with the virtual machine on top of it, right in here. So you've got your virtual machine, like your virtual box I showed you here. This machine, this is a program, right? This is a program that's running on the host machine. So this program is right here, and it's talking to the host operating system to the hardware. And this little, there's a word for it, hang on. Interface. I think you would call this an interface. Script, let me think about what terminology. I can't come up with the software concept from a programming perspective, but it's an interface between the kernel that runs in this environment and your actual machine that's supporting it. And I think Boomer's probably right on through the hypervisor. Not sure if that's called that, Boomer. But did that answer your question, Mega? Okay. Okay. How much memory I've got on my machine? Yeah, I'm still doing okay. I'll just leave that. Good questions. Is it a shell? I don't think you refer to that as a shell. It's just eluding me right now. It's not an API. You don't come to me. You've got overhead involved on any of these operating system designs. So in the case of a simple batch overhead, the processor time alternates between execution of the user and execution of the monitor, of course. And a lot of what we're going to talk about, guys, it's easier to think of just having one processor. Is it a driver? Yeah, it could be considered a driver, but it's really more of an interface. It's not an application program interface, but it's an interface between let me think a second. It's an interface between this request from the operating system being formalized and switched to a request that this guy can process. So in one way, it's an interface. It could be a stub. That could be the word that I'm looking for from a programming perspective, is a stub. That's what this might be, is it's a stub. Okay, yeah, I finally found it. It took me a while to think of it, but that's what this would more likely be. Okay. Okay, so the idea is you're going to alternate between user programs and execution of the monitor. And what I was trying to tell you guys is it's much simpler in our examples until we get to multiprocessing. It's much simpler to think of a single processor. So even though we know that there are multi-core processors, let's just assume we have one processor. And then when we talk about how to manage multi-processes, let's talk about it then. Because it's easier to think of one processor. Let's see. So if I have a multi-program batch system, I could be read one record from a file, it takes 15 microseconds. To execute 100 instructions, it takes 1 microsecond. To write one record to a file, it takes 15 microseconds. Total of 31 microseconds. And then you can calculate CPU utilization as an example. The processor, during reading or writing a record, the processor could be switched to doing something else. Okay? And that's what we're going to be talking about. I/O devices are slow compared to the CPU. So in this case, it's 15 times slower. So uniprogram, right? Uniprogram means you're not multi-programming, you're running one program at a time. And I gave you an example of that. That's DOS. You run one program at a time. Let me see. Let's open up and run DOS. Okay, and I showed you last time, let's go to the C drive, I showed you Q basic. That's a program. It's running, and I can't run any other program. I have to stop this program, Alt-F. Let me capture Alt-F. Oh, I need to get by this screen. Alt-F. Exit. Now I close that program, and I can run another program, like fdisk. Right? I showed you fdisk, and I can only run fdisk. Now I can run another program, and you see the issue here with unique programming. One program at a time. It's a waste. And what you're wasting is CPU. Waiting for the I.O. to complete, run it, waiting for the I.O. to complete, so you're really wasting CPU. Multi-programming, you can run program A, wait for an I.O. While the I.O. is going on, you can have the CPU run something else, and it could wait. Okay? And this environment is what we have today, and this environment is what we want today, and this environment creates all kinds of interesting issues, and those are what we're going to be discussing. What are all the issues in a multi-programming environment? When you run this way, this is called also multitasking. I told you my definition of multitasking is a little different than these books' definitions. They're showing as jobs, right? And they're just showing you how long the thing's going to run. 5 minutes, and then how much memory is required, need disk, need terminal, need printer, yes, no, all of that, because we need to manage that environment. And what you're looking at right here is the start of the extra credit problem, that if you wanted to work the extra credit problem, it involves one of these kinds of concepts of multi-programming given certain characteristics. Like I said, I'll discuss that when we have a block of time to discuss that. And you can see how much resource utilization is done. In UniProgram, the mean response time is 18 minutes of this, and it's 10 minutes on this environment, and the total elapsed time is 30 minutes, and multi-programming is half the time. So you can get a feel of why we went to multi-programming. I'm going to move on. Time sharing. Typically, the concept of batch versus time sharing. Think of it this way. Got a lot of notes, so I'm going to have to go over these notes here at some point. Think of it like this. Batch jobs are one or more programs are run without user intervention. That's what batch really means. So something can execute without the user intervention. Whereas timeshare is more online. So I'm going to say this. Timeshare is more interactive with the OS. You're really interacting with the OS, and you want results immediately. In other words, you want to be able to, as you're typing like here in Notepad, I'd like to see it happen at that same time. Whereas a batch job is you create a whole bunch of batch functions, and it would execute at one time. I can illustrate that if you'd like to see a batch job run. We can do that in about, I don't know, a few minutes. Let's go to DOS, right? And let's edit. That's a program. Test that. So we'll echo off, turn echo off, and let's do directory of the C drive. Let's change directory to the A drive and do the directory of the A drive wide. And then let's echo goodbye. And that should be a simple, so let's do Alt-F, save, Alt-F, exit, and let's type out testbat, see what's in there, and now let's just execute it, and it just did. Okay, it showed the directory, it changed the directory, and then it showed why. You don't see the commands. What you see is the result of the commands, and then you see the echo goodbye. And all of that came out of this batch file called testbat. And that's what it did. It did a directory of C, changed directory to A, did a directory of A, Y, and went back to where we were. Does that make sense, guys? Is that clear? That's batch. There's no interaction to the user. Okay. The time slicing or time sharing systems, they were big in the late 80s, but the mainframe had time sharing. It was called CIS, CIS, Customer Controlled Shareable System, or something like that, a Customer Information Control System, CIS. And it was a great product, and what you did was it allowed you as a programmer to write programs that run on the mainframe that the user can see at the terminal. This would be a terminal, dumb terminal. They had dumb terminals at that time. And then the program ran, and it did this time slicing concept on the mainframe. And then what happened was DEC also started doing time slicing, and allowed users to log on to the system and get results. Today, we have exactly the internet, and the internet is nothing more than a time sharing or time slicing system. That's how it works. Matter of fact, the browser, if you think about the browser, well, let's get a browser up. You think about a browser today, right? And let me go to Google. And that period of time that the browser sent the request, it came back. This is a dumb terminal, if you think of it that way. I mean, it's smart because it's a program, but that's how terminals were in the 1980s and 90s. So basically, the internet is nothing more than a little more sophisticated dumb terminal. Okay, I'm going to keep going here. Is this helping going over this other presentation with you guys? Is that helping you understand? Or am I kind of wasting my time? What do you guys think? It helps. Thanks, Albert. Thanks, Albert. Anybody else? Okay, very good. Well, if it's really helpful to you, do you want me to post this on Canvas? Okay, I'll do that after. Sure. This is a true statement. Operating systems are among the most complex pieces of software ever developed because of all these things we've been talking about. So, fundamental structure. First, you have to define what a process is. In our book, Chapter 3 defines process. In this book, he defined it here in Chapter 2 in this presentation. Okay, a program in execution, an instance of a running program, an entity that can be assigned to or executed on a processor, a unit of activity characterized by a single sequential thread of execution, a current state, and an associated set of system resources. Those are all different definitions of a process. I kind of talked about these before. Multi-programming, time-sharing, and real-time transaction systems. We'll kind of illustrate real-time transaction systems. I think it's in chapter 13. I don't think we do 13. But if you really wanted to, you can take a look at chapter 13. I skipped doing real-time systems. I'm going to skip over this. The reason is we're going to cover most of this stuff when we talk about processes in Chapter 3. Another issue is memory management. So another thing of the operating system is how do we handle memory management? And you have to have process isolation. You have to have some way of allocating and managing memory. You want to be able to support modular programming. And you need to protect and access control. And you need to have some mechanism for long-term storage. All of that is part of memory management. Virtual memory is chapter 9. 8 and 9 is dedicated to virtual memory, and it's a big one, important. We'll discuss it. I'm going to skip over this because what we're talking in chapter 2 is all the different high-level stuff. Information protection. You want to be able to protect. You need to authenticate that the user, right? You need authenticity. You need to keep the data integrity so it's not corrupted. You need to keep it confidential. And you need to keep it available to those that are authorized. So these are the main issues of protection and security. We'll discuss those in chapters 14 and 15. Do you remember what these go to? What do you think these three things go to? What did we start out with in this slide presentation? Do you remember? Yes. And we said that the designers have what in mind? What are the things? 4 letters. Well, with an S, it would be 5 letters. Yeah, purpose is close to the idea, Kang. You almost got it. Starts with G. Yeah, excellent. It's the goals. If you go back and look at the goals, these are the goals, and of course resource allocations must consider these. Very good, very good. Chapter 3 covers this, so I'm not going to worry about it now. You have different approaches to designing things, and they've been tried. Microkernel architecture, multi-threading, symmetrical multiprocessing, distributed operating systems, object-oriented design, and in today's world, what do we have? This slide's probably about 10 years old. Design patterns, good, Mega. Dynamic programming, another good one. Good. So there are other ideas that have come along. I think that's what this slide is trying to tell you. I'm going to skip over these because we're going to talk about them in depth at some point. This is just another way of looking at a multi-programming, right, where one program over time is using the processor, waiting for I/O, using the processor, waiting for I/O, using the processor, using the processor, using the processor. So what happens is, in a multi-programming environment, is if the I/O is completed, then it has to wait to come back and get the processor. And we're going to talk about that in chapter 3, 4, 5, 6, and 7. All of how to handle that environment. It's really fun. Probably the most fun is chapters 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. They're real fun. Yeah, it's awful good too. Then he kind of talked about the distributed system and object-oriented design concepts. The latest of Windows has been moving towards this for some time. I think in the 90s. I remember object-oriented programming coming in late 1980s, this concept. And distributed systems came in the mid to late 1990s, these concepts. We talked about this a lot, so I don't need to talk about the virtual machine. I don't want to talk about those. It's kind of good to review. So let's take a quick look. I've been on all these operating systems. The original DOS, and the last DOS was version 6.22. Was the last DOS release. Windows 3.0 was crap, and 3.1 was just a little bit worse. Well, it was a little bit better than 3.1, 3.0. And then Windows 95. You see what happened is it kind of moved from a 16-bit architecture to, in Windows 95, meaning 1995, it moved to a 32-bit architecture. Windows 98 was crappy, and Windows Me was crappy. NT was the first really good Windows. Okay. But the problem with NT, does anybody know what NT stood for? No one knows? That's okay. It's not going to be on a test. New technology. Real sophisticated. And let me stop and explain this to you guys, because it's really important. I mean, from a historical perspective, to get an understanding of where the operating system has come and where it's going. In my thinking, OS/2 was IBM's product that Microsoft was building for IBM, and in the 1980s, and Microsoft really gave IBM the shaft on this one. And here's kind of what happened. Windows was being built in the late 1980s and early 1990s. And OS/2 was being built by Microsoft for IBM, and it was targeted to be a server. You know, multi-programming, all of that as a server, high reliability, all kinds of things, OS/2. And the concepts came from the mainframe. The mainframe was around for, at that point, since the late 1960s, IBM's 360 architecture. And from the 1960s to the 1980s, what is that, 20 years, they learned a lot. And so they told Microsoft all the features they wanted in OS/2. They wanted a kernel, they wanted the protection, they wanted this, that. Everything that you would want an operating system to have, they built it in OS2. And what Microsoft told Bill Gates, basically told IBM was, well, we're building Windows to be desktop, and we're building OS2 for you to be servers, and we're never the domain will meet. In other words, we're going to stay in the desktop domain, and because we're writing OS2 for you, it'll be your product to sell and make a lot of money. Well, guess what happened? Windows got more sophisticated. 95 was a lot better, and IBM saw the writing and said, "Oh my God, you guys are really, doing it to us. So we're pulling out. Give us the code." And they did. Microsoft gave IBM all the code for OS2, but they didn't take the programmers that created it. They were Microsoft. So guess what NT looks like? NT looks exactly like what product? It's not called that, but it sure is designed that way. You can tell me, Albert. Anybody? OS2. That's right. NT was really OS2, and that's probably why they called it 3.1, because it's not 2 anymore. It's 3.1. They really jammed it to IBM. And then, of course, IBM got out of that world, and eventually IBM got out of building computers, PCs. They sold that business line to some foreign company. Anyway, it was really fascinating to watch, as I was a manager at that time. Yeah, thank you. I couldn't remember the name. Thanks, man. But that's what NT is. And the Windows 2000, what do you think's at the bottom of it? The NT architecture. XP, NT architecture. Vista. Vista was the first one that was supposed to be built from the bottom up, and they couldn't get it to work. So they went back to this architecture, the NT kernel. And then the Windows Server on top of it, Windows 7. By the way, I'm running Windows 7 on my desktop right now, and it's been really good. I've been very happy with this. My poor wife has 8.1 on her machine, and it is really awful. I'm really sorry. And she's always telling me that my machine doesn't have any issues and hers has lots of issues. It's not hardware, it's the software. Now, Windows Azure, right, targets cloud computing. I'm not sure what's going to happen with that. I'm moving on. See. So in the kernel mode component, right, you've got your core OS services, you've got your kernel, and you have a hardware abstraction layer. The reason for this is you need to have a layer between the hardware and your programming specifications, so that it makes it easier to deal with changes to the hardware layer. And then finally you get device drivers that are basically extended functionality of the OS. And then on top of it, you've got your graphical user interface. So all of those are kernel mode type things. 4 basic types are supported in user mode. Special system processes, so you can manage services, right? Services need to be managed by the system, but you can control some of them. The printer spooler, I'll talk about spoolers at some point. Then you've got your subsystems. Now the subsystems are all your environment underneath the OS that support user applications. And then finally, you've got user programs and DLLs that support user programs. And we'll show you DLLs and what they do. I'm not going to do client-server model because that model is pretty much gone. I don't think people are still using this model. Today, it's wide area networks. Boy, I like this diagram. Remember we saw this earlier in the other, but there were no names, right? There were no names in it. They were just layers, right? And this is an example of a layered or modular operating system. And you're definitely going to see this again. I think I've showed you this in the other slide presentation. It was four layers here. I might not have. Maybe that's in chapter 3 in Silvershot's book. Has anybody used Linux or is using Linux now on their machines? I thought a couple of you guys had Linux. Anybody? Let's see, I didn't say hi to Vincent. I'm sorry, Vincent, I missed you coming in. Steve, I missed you coming in. Rial, I missed you coming in, sorry. Bang. Danielle, I missed you. Dale. I think I got everybody else. Boomer, yeah, I thought somebody said last time, Linux. And you're using what version of Linux? What distribution? Fedora, Red Hat, Ubuntu, Slackware, any of those? Fedora. Yeah, that's Red Hat, isn't it? Red Hat's Fedora. Yeah, I've used Fedora. I've got an older version of one of my machines. CentOS too. No, I'm not familiar with that one. Yeah, the first distributed Linux that had a distribution was called Slackware, and it was in early 1990s, and I got involved in that. That was a lot of fun. Okay, I'm just kind of going through this now. We'll talk more about this stuff later. Let's just look at the summary, and then we'll take a look a couple of other things I've got, and then we'll call it a night. First, operating system objectives and goals. Very important to know what they are. From an evolution perspective, how things happen. By the way, this is not on the test because the other book didn't discuss evolution, even though I'm kind of discussing it. You have to manage the processes, multi-programming that whole environment. You have to manage memory. There's a concept between real address and virtual address, and we will address that in chapters 8 and 9. Scheduling and resource management. Chapters 4, 5, and 6 deal with processor scheduling. Memory management scheduling is in 8 and 9. Multi-threading, or multi-threading, what that is with the concept of threads. By the way, the concept of threads came along with OS2. OS2 had a threading model, and we use that today. Linux started to use multi-threads, but they still call them tasks, I believe, multi-tasks. Symmetrical processors, we'll learn about that. And then I talked a lot about virtual machines and virtualization. And I highly recommend you trying that. Okay. Let me go to my notes. I saw a whole bunch of stuff. So let's see what the heck I was saying here. What's multiprocessing? Anybody? That's a good guess, Mega, but that's not quite it. Yeah, that's correct. Albert, Dale, more than one CPU is multiprocessing. More than one CPU. You're managing more than one CPU on your machine. Multi-programming. You're allowing what? Multi-programming. Key concept. Multi-programming. Okay, is Notepad a program here? Let me answer that, yes or no. Anybody? Is Notepad a program? Yes or no? Yes, Mega, what do you mean no? Yes, it's a program. Okay, is Internet Explorer on my machine here, is that a program? Not an application? Well, don't get confused about applications. Is it a program? Yes, it's a program. So, in this environment, do I have multi-programming going on? So, what's the definition of multi-programming? It allows what? Running multiple programs concurrently is the terminology, but we know for a fact that it doesn't run concurrently. It runs on one processor, it runs somewhat concurrently. But the concept is multi-programming, allowing more than one program to run at a time. multitasking concept was in online, getting results immediately. Programs and processes are the same thing, Rial. A program is equivalent to a process. What's confusing is the word application. Steve, no, I don't think so. I don't think that's a direct result. When you have one CPU that allows more cores, right, you would have multiprocessing. Multiprocessing has to do with the hardware. I have more than one CPU. Multiprogramming deals with the software. I'm running more than one program at a time or more than one process at a time. Is that clear, Rial? Yeah, the core is multiprocessing. That's correct. But remember what I said that we need to assume here when we're talking about multiprogramming can have one CPU or more. All right? Because what the concept is of multiprogramming is the operating system supports running more than one process or program at a time. That's multiprogramming. The definition of multiprogramming is the operating system allows more than one program to be executing at one time. Multiprocessing means there's more than one processor the operating system is managing. Good. Okay. The difference between privileged versus non-privileged modes of the CPU. Privileged modes are instructions that only the operating system can execute. Non-privileged modes are those instructions only allowed by the user programs. Okay, so once again, privileged instructions are ones that operate all memory, all I/O, all users, etc. Non-privileged instructions are ones that add values to registers, branch to locations, request service from the operating system, etc. They can't touch the hardware. So the operating system has to keep these modes of the CPU straight. And in Chapter 3, I'm going to illustrate how that works together. User mode versus kernel mode operating system. Okay, so basically, when I want, as an operating system, I want to have the user run, I go to non-privileged CPU mode and let it run. Okay, then when I'm in kernel mode, and the hardware will flip that to kernel mode, and it'll flip it to privileged instructions, and I can execute any instruction. Okay, Intel's protection modes I went over last time. 0 is kernel level, and all instructions are allowed. But the operating system's too complex anyway. It never implemented these concepts. It's either 0 or 3. So user program is level 3. And then when it flips to kernel mode, right, it goes to level 0. And it always starts at level 0 when it goes to kernel mode. And it flips it to 0. And once again, I'll show you exactly how that works with the CPU interrupt mechanism. And that's what you need to understand. Okay, I gave you on the very first day how memory works. Tri-state logic. It's either a 1 or a 0, or it gets off the line. And what we're saying by it gets off the data line. So it either puts 1s and 0s from memory on the data line, or it gets off of it. So during a fetch, the address lines are active, and the data line is waiting for the last pulse to be clocked. I illustrated that so that when it clocks that data line, it's accurate because all the rest of memory, except what was requested in the address lines, all memory is off the line. So the only thing on the line is that address that the address lines have indicated. Do you remember that on Tuesday of last week? How that worked? Good. Okay, I illustrated these tonight too. I illustrated machine code. That was here. I illustrated that with this virtual machine, Windows XP. These are machine instructions. This is what the CPU will execute, these instructions. This is the assembler, if you were writing assembly and then having an assembler convert this English-like language into that machine instruction. That's machine code. I had an illustration somewhere. Hang on a second. Did I have it here? Pentium 4. No, I didn't have it there. Let's see. We're almost out of time. Anyway, I showed you an assembly, what it would look like, and then compilers, high-level languages. There's a lot of them. Three different types of user interfaces. I mentioned this, I think, on Thursday of last week. Command-driven, menu-driven, and graphical user interface. And we're all familiar with this now. I talked about interactive and background. Background is like batch. Something runs in batch because there's no user involvement. So the word background or batch really became, in my mind, background because there's no user involvement. Batch mechanisms. Okay. Let's see. Oh, I should have mentioned this on the first day. I feel that we have three paths of learning the material. My lectures, my 2-hour discussions, my experience, what I think is important. The book reading, other views of material and other views. And then the discussions and the project. So you guys will be doing the group project together and the discussion forum. So those are the paths, and anything else you can do would be great, right, to experience. I mentioned this last time, or the time before, about the cycles of the CPU. You should know the cycles. On ROM, when the machine boots up, there's the basic input-output subsystem that's on ROM. or double EEPROM, and it gets executed at startup time to boot up the system. Typically, there's in main memory, there's something called shadow RAM, because usually RAM is faster than ROM, so it copies this, and that's where shadow RAM is talked about. And it's in the BIOS setup. Finally, this basic input-output loads the loader, and that loads up the rest of the operating system. Okay? And in Windows, it's the NT loader program that does that. And I think that's it. I think that's everything that we talked about. Are there any questions? Just confirming the project is optional, isn't it? Not this project. This is the team project. There's an optional project. Yeah, maybe I should put number 4. Extra credit. Which I'll introduce at some point. So why don't we say 4 pass? But it's optional, so I don't know why I put in it 4. It's 3 plus 1. How about that? Kang, is that clear? Yeah, when I mentioned project, I should say it's the team project. And I'll try to always say extra credit programming project for the other. You know, Three plus. How about that? I don't know what happened here. I put in the URL. That's what happened. I put in the URL that I gave you guys earlier. Okay, I think we're pretty much wrapping up. Any last minute questions? So, Thursday, when we meet, it'll probably be a shorter session than we did tonight. I'll review kind of the items that you need to understand for the test. It opens on Friday. I'll do the CC Confer with you on Thursday so you can answer that. And you've got homeworks 1 and 2 due this Friday, Sunday. So this is Sunday, and these 2 are Sunday. Those are due. Any other questions? Thank you guys. I really appreciate your help. And I hope it's becoming clearer to you now and getting better. I'm going to turn off desktop sharing. And I'll look forward to seeing you on Thursday.